Perfectly fine. Thank you. Okay. Well, it's a great pleasure to be here. I've been at Isaac Newton Institute a number of times, and it's always great fun. It's a little harder than I remember it from 2 years ago, but still fine. So I'll speak about Koopman operator methods in dynamical systems. It's going to be 3 lectures total, and in the first lecture, I'll introduce some of the basic concepts, maybe talk a little bit about the history at the beginning. I'll tell you the plan in a moment. But one thing that I wanted to start with, and I'm glad Steve started with it in the morning, is what can be done with it. And so Steve spoke quite a bit about fluid mechanics examples. I'm going to show you 3 different examples of what we are aiming for these days, just to kick it off, and then we will do mathematics for the rest of it. But I just want you to have a vision of what kinds of things can be done in engineering these days. So the first one that I'll show you is this. It's a soft robotic arm. It's made out of cloth, and what you're seeing on its body is LED diodes. And what you're seeing now is what we call the training session. So you're just moving it around randomly. I compare it with a baby in a crib just waving its arms, trying to figure out its own model. When we did this, I thought, oh, that's what babies do. They are trying to figure out their own model. Try to figure out the Koopman model, and then once it figures it out, you can give it various stacks. So you might find this exhilarating or creepy, depending on your point of view, but it's following a stick, right? And it's doing that very well. I can show you some more examples of what it's capable of doing. This is another one just to show you that with a 5-minute additional training, you can do another soft arm. 5 minutes, I said that. So not a massive data center with a nuclear reactor attached to it, but 5 minutes of training on the CPU. And that is kind of an interesting aspect of this whole approach, that it is capable of doing these kinds of things, but it's following the stick right now. It does more fun things. It catches and throws balls. Now, let me see if it will. There we go. It's a little bit, okay. So that's that. I couldn't resist this one. This is a Premier League match. Not all the players are pictured in red and blue, but you see that there was a goal happening. That is the ball, and very light. And this on the bottom is the Koopman model kind of prediction of where the ball should go. And right there, you're seeing that it's predicting with reasonably high quality that, in a percentage of plays like this, the ball is going to end up in the goal. I couldn't resist this because of the World Cup. That was. There is no referee. There is no referee on this because we have to kick out the referees, or at least VAR, in my opinion. Okay, I didn't just say that. Out with Infantino. That's my political statement for today. Yes.
I'm a Spanish, so I'm happy with that.
Congratulations. You do have one player that trained in Croatia, almost, so I'm happy with that. The third one over here is just a recent one that Matt really brought about, and it's both a study of limits of what you can do, which is also important for us, right, in mathematics. The study of limits, what you can really do with these methodologies. It has some elements of, talking about why do neural networks hallucinate and things like that. That's maybe a little bit of a speculation, but one of the things that we were able to do quite well is show these sea ice modes in the Arctic and the Antarctic as well. But you see in blue those dots. These are the eigenfunctions that Steve talked about today in the morning. But they're actually computing using a rigorous algorithm that says that if something's there, we will show that it's there with residuals and with kind of precise limits, right? So one of the things that distinguishes us from, I would say, a lot of the machine learning approaches is that there are deep mathematical foundations of how exactly to do things. Also, and give us limits on how to do things. Also, try to get Claude or ChatGPT or Gemini or whichever other DeepSeek, whatever other model you want, to do time series prediction. Try it. They're really bad. So transformers are really bad at doing time series prediction. There was a whole NeurIP session 2 years ago on the fact they're still not there. The interesting thing is that you can do predictions on CPU, and this is what Matt is showing over here. The yellow curve is the lowest error. That is the proposed method, which is a Koopman-based method. And here is IceNet, the best neural network predictor that exists out there. And you see how interestingly long-term prediction the Koopman is capable of doing. So I'm showing you this to give you an impression of what we are capable of doing, also with rigorous limits on what we are capable of doing. The most complicated thing, something that Steve didn't talk about this morning, is aspects of chaotic dynamics and continuous spectrum. But I will start with eigenfunctions as well, and then I'll lead into discussion of continuous spectrum and the associated problems. So here's the plan. I'll start with some basic 3 points of view on dynamical systems. I'll tell you that the Koopman operator unifies those points of view. We'll define it. We'll talk about the algebra of Koopman eigenfunctions. This is actually quite important because if you go to functional spaces in which you can compute dissipative processes, so these eigenvalues that are not the stationary eigenvalues, but they're describing decay to the attractor, then you need to change the functional space from L2. This is quite an important point from mathematical perspective, but also from computational perspective, because if you actually don't change the point of view, as Steve pointed out, you cannot compute those rigorously. There is no way you can compute them, right? You will be computing something else, probably something in the continuous spectrum, but not the eigenvalues themselves. Now, in my own program, I was always interested in the geometry of dynamical systems. When I was a grad student, Tony Leonard, who is here, was my co-advisor, and I think he was scratching his head a little bit when I said, oh, you can get some of the geometrical properties of this from this operator. Because most of the work was on unstable manifolds, geometry of these. I still love that, and so I will try to connect it in the talk. So the connection between the functional analytic operator theoretic aspects and the geometry that we know and love is going to be there. And then I'll talk about linear systems, eigenfunctions, spectral expansion, Koopman mode, so that you can very vividly see what it means when you're at linear systems level, right? Took note from the Hirsch and Smale spending about 80 pages of their book from, some of you probably don't know this, but the Linear Algebra and Dynamical Systems book by Hirsch and Smale is a very beautiful book, but they spent a lot of time talking about linear systems, so I'm going to do a similar thing. Okay, so here are the standard points of view. It's very appropriate that our beginning starts with Isaac Newton. Here we are. But the point at that time was to try to get the harmonic oscillator solution, a solution given initial conditions and time, right? You have an ordinary differential equations, you write it out as some kind of a closed form expression. Now, of course, that's limited. Poincaré told us this because on the three-body problem, you cannot get a closed form solution of this kind. That led to the whole study of chaotic dynamics. Later on, in the simple case, this is what the state space looks like. You're studying x versus x dot, so x and y. So you took time out of the picture. You actually replaced it with a state space, or as it's called in physics, phase space. Control theorists use state space. Physicists use phase space. Now there is a third point of view which is rarely talked about, but it might belong to Wiener, right? I think you can take it all the way back to Fourier. If you have a signal that looks like this square wave in yellow, then if you have an oscilloscope in the lab, you can of course look at the frequencies that are associated with that particular motion. You might have a base frequency and harmonics. It is quite interesting that in that case, if you rewrite that solution as sines and cosines, you will have three quantities, A, omega, n, and phi, so the phase, frequency, and amplitude, to worry about. And you can reconstruct the whole time evolution from 3 numbers. Compression, anybody? This is where we get pretty much all the compression that you know today, but that occurred a long, long time ago, right? So if you're able to do this for general nonlinear systems and try to understand the spectral aspects, which is amplitude, frequency, phase, you have ability to condense the information and perhaps predict and do a variety of things in the future. So I'm going to argue that all of these are contained in this larger picture, an operator theoretic picture, from which if you distill it down, you can get elements of the other 3. So hopefully I'm going to be able to convey this in these lectures. So let's talk a little bit more about the Poincaré view, the state space. X dot is equal to f of x. The flow is st. So that depends on the initial condition. And so the idea that Poincaré brought about is let's draw theta versus theta dot in this pendulum equation here. You've all seen this before, right? So, okay. So I'm just trying to convey a couple of points on the Poincaré picture. Here's the vector field. Here are the stable and unstable manifolds, the fixed points. All of these appeared in Poincaré's works. And the point is, you don't need to solve the equation. You need to look at the right-hand side, and you can qualitatively conclude things about the equations from the right-hand side. Yeah, that was the general point, if you can find these objects. But there is another point, and that is that if you write down f, the flow field, dot grad h is equal to 0, that function h is an invariant of the system. Okay? Poincaré perspective doesn't change. F is there. I don't need to solve for the flow in order to solve this PDE. Steve said it's a horrible thing to solve. However, in special cases, if you have a Hamiltonian system, for example, which this is, then you can just write down the energy and you have an invariant. Right? I will show you that this is directly correlated with the generator of the Koopman operator. And in that context, the first thing that you learn, well, one of the first things that you might learn is that the zero eigenspace of an operator, linear operator, immediately gives you energy. And you might ask yourself, well, how about other invariants or other things that are in the eigenspace, right? So to a certain extent, and Poincaré spoke about this at his lecture at International Congress of Mathematicians. He said, look, you know, these PDEs are actually encompassing some of the aspects of well, all of the aspects in principle of the nonlinear dynamics, but the question is, can you extract things from it? As Steve pointed out, this is hard to solve, right? So we'll find a way around it. And that way around it is relying on spectral understanding of the operator that I'm going to define pretty soon. So here is the definition. If you have some system, x dot is equal to f of x, and I will abandon this idea as I go on. In the third lecture, I'm going to say, is there a system such that x dot is equal to f of x? You will see. So I'll flip from saying, I have a system, I want to analyze it, to I have data and I want to model it. That's lecture 3. But if I start with x dot is equal to f of x, strictly speaking, this is what Koopman observed on state space M. And then G is some observable. In this case, it's a vector observable and it's complex. You immediately want to go with a complex analysis because your eigenfunctions that I will define might be complex. Define the Koopman family of operators. U, T up there, acting on G. Is G composed with a flow? So you have a flow down there. You have this function G. In this case, it's scalar. You evaluate its function. You go further with the flow. You figure out what the observable is, you pull back. It's a pullback operator. In differential geometry, you would call it a pullback. It's linear immediately because composition is a linear, basically a linear operation. That it passes through, right, the addition and the multiplication by a scalar. And so any self-respecting applied mathematician is going to say, what's the spectrum, right? There is, see a matrix, you want to know its spectrum. If you see an operator, linear operator. So So you get a linear operator that, as we will see, describes pretty much all the dynamics for any observable, be it energy, be it linear momentum, be it angular momentum. It's going to describe every observable, not just the original observables that Isaac Newton gave us. It's going a little bit beyond that vision of having a state space, having X and the momentum, right? The brilliant observation that happened here, that the change of momentum is equal to force. But clearly people came up with things like energy, angular momentum, and things like that derived from the mathematical analysis that told us that there are observables that are also quite important, and we talk about them. We talk about energy all the time. So we talk about energy a lot more. If I say to someone momentum, then they're going to think momentum in a game, not linear momentum or angular momentum. We talk about energy all the time. That's the concept that actually penetrated the kind of general public consciousness. Position and momentum, well, for us, yes. So here is just a little bit of history. Koopman's paper in 1931. That made quite a bit of impact in what's called ergodic theory and statistical mechanics. So von Neumann was a friend with Koopman. They wrote a paper together. Then von Neumann said, oh, if I have a very large dynamical system, 10 to the 27 molecules or something like that, can I prove that the time averages that I'm taking of some observables in that system, for example, energy, actually converge? And von Neumann proved that in the mean. Birkhoff used Koopman's formulation. That was a massive deal at the time. In the lectures on statistical mechanics I took, this was mentioned in the first lecture and forgotten. Sometimes you never need to justify that time averages converge, but for people in mathematics, it's important. What is really interesting is, I'll come back to that, is that today we are using a different version of convergence, and that's Birkhoff's, that von Neumann had a very low opinion of, by the way. People can be wrong. He said everything in the mean is perfectly fine. You don't need pointwise convergence. But if you want to do analysis from a single trajectory, then you need pointwise convergence. You need convergence from almost every initial condition. And then Kolmogorov in 1954 actually promotes this. And then there's a whole sequence of students of Kolmogorov, Sinai, Arnold, and others that poured this picture forward. Now there's a whole other beautiful set of works that are summarized in this book on the composition operator itself. And this is usually done on unit disk in the complex plane. So for the applied context, these works can seem esoteric because they're not on the types of spaces that we know. But as I'll point out later on, when you go to dissipative systems, you sometimes need to complexify, and you basically get to things like Hardy spaces and Bergman spaces and things of that sort. So the functional analytic aspects of this, despite the fact that they were not present here, it's all in L2, actually come in, and they end up being quite important in various different ways. Julia has done some really beautiful work in kind of changing the functional space and figuring out the AD&D works for those contexts if you change the functional space, if you're not in L2. And that's one big topic that I think to a certain extent is not, well, it's really being discussed at a large scale right now. All right, there was a quiet period. There was only 100 citations. This is in Claude, by the way, so don't blame me for the history. I asked Claude to give me the history. So I knew a large part of this. Well, I corrected it based on what I knew, but actually, for that kind of stuff, it's pretty accurate. I'll make a statement. People are claiming, conjecture solved every day, and I believe it. But I find it that if you're working on a new problem, then it has almost no power to a certain extent, right? All right. It shifted to Lorentz. There are some works in early 2000s it ported to applications in fluid mechanics that Steve talked about, power grid dynamics. EDMD showed up. Dimitri Giannakis did compactification. Claire is here somewhere. And then now it's kind of a big thing in control theory. Strong ties to data-driven machine learning. Steve, Nathan, Enoch Young, Kawahara, and so others. And about 80% of the thousands of citations to Koopman's paper are actually from the last 20 years. So the main idea is represent your nonlinear dynamical system in an infinite dimensional context, and then see what you can do with it. But the key is to find finite dimensional representations, as I will point out through the lectures, right? So let's start with something extremely simple. I'll show you two super simple systems that you can construct a lot of other systems from. The first one is z dot is minus lambda z, lambda is bigger than 0. It is a stable equilibrium. The flow is st is equal to z0 e to the minus lambda t, but it carries one really interesting aspect to it, and that is, if you pick that your phi of z is just z itself, so you're just observing the state itself, that is clearly an eigenvalue minus lambda. I mean, eigenfunctions satisfy phi dot is minus lambda phi, so that is an eigenfunction, right? But so is, for every n, phi of z is equal to z to power n. And you might ask, well, why? It's a linear system. Why in the world do I need all these other eigenfunctions? Well, let's suppose that you're measuring z, but your sensor does something like this, which every sensor does. There is no sensor that is linear that is going to measure just z, maybe around the equilibrium, right? So it saturates here. Can you represent this observable here? The observable, your measurement, using z only? No. But you can certainly do well, if it's smooth enough, right? You can certainly do a Taylor series and represent that measurement using all the eigenfunctions of Koopman, yes? So even for linear systems, if you're an engineer, the Koopman analysis is actually important because it gives you these additional elements that you need to incorporate into your measurement understanding when the measurement is nonlinear. So that's one system that is really, yes.
So you're saying that if you want to reconstruct your measurement using eigenfunctions, then you need these to the end.
Well, so there is more to the story, right? It depends on which functional space you're really in. If your measurement is analytic entire, then you only need z to the n's. Now, if you have something like z to 1/2, well, good luck. You might be in the continuous function space and you need these as well, right?
Yeah, sorry, I just missed the main thrust. So you're saying, is the purpose to generate the measurement with the eigenfunctions?
Yes, if you want to understand how your measurement is evolving in time, under linear dynamics, but nonlinear measurements, then you need other eigenfunctions here. All right, so there is a theme here because z was the key eigenfunction, right? So phi of z is equal to z. So that's the first one, and that's what we call the principal eigenfunction. Now, if you multiply that by itself, you get another eigenfunction, z squared, and so on. That's not by chance. You can easily prove that if you have a functional space that is a commutative algebra, so you have functions that are in a space where you can take products and they commute, of complex valued functions on your state space, then the eigenfunctions form what is called an abelian monoid. The only thing that you don't possibly have is the inverse. If you have the inverse, then it's a group. It's a very beautiful algebraic property that allows you, practically speaking, to do Taylor expansions. Because you can take z squared, z cubed, or in n-dimensional space, you can take products of things and get to Taylor expansions. And I'll show you examples of this. Now, I promised two basic systems. So the other one is theta prime is theta plus omega on the circle. So the first one was everything goes to equilibrium, and then the other one is just jumping around. This is in discrete time. Instead, jumping around on the circle with angle omega. That one is rotational. This one is dissipative. It turns out that you can represent up to chaotic systems. You can represent pretty much anything by a product of these two things. So think about a toroidal attractor with some kind of irrational rotation on it and dissipative dynamics to it. You basically get that kind of a structure. Now, the reason why I wrote this here as the space, the Wiener algebra, is that L2 is not enough for me to tell you the story that I gave you in the theorem. Why is that? Because L2, of course, is not an algebra. You multiply two functions and you get something that is not necessarily square integrable, yeah? The Wiener algebra is, but it's defined spectrally, right? By the coefficients in the Fourier expansion being summable. And in that space, you have these perfectly nice eigenfunctions that are just harmonics, e to the I k thetas. As you can see, if you have theta plus omega, just count the multiply, right? You put theta plus omega here, e to the I k omega comes out, multiplies e to the I k theta. You have your eigenfunctions. You can represent any L2 function in it, but also you can represent any function that is in the Wiener algebra in it as well. I'll say, for those of you that are more interested in the functional analytic aspects of this, I just wrote a paper for the operator theory, a little handbook that has all of this stuff in it. If you're interested in it, send me an email and I'll send you the. Okay, PDEs. If I have sufficient regularity, meaning there is uniform continuity for the underlying operator semigroup, then I can kind of differentiate the evolution. So I take UTG minus G, take the limit when t is equal to 0, and I get on the right-hand side f dot grad of G. That's precisely what I had when I talked about the Poincare deduced PDE, right? So I had that invariant f dot grad H is equal to 0. But this here is what is called the generator of the Koopman evolution UTG. So UT, remember, is the composition is G composed with ST. The generator of this is this dynamics. What does that tell you? That tells you that the change of the observable that you're seeing at this point here is obtained as what is called the Lie derivative, or the change of the function in the direction of the vector field. Yeah, that is change in the direction of the vector field. A direct connection to geometry there, right? They're talking about Lie derivatives now, which is not functional analytic concept. In the case if your f is globally Lifshitz, you have existence uniqueness. Your UT is going to be a group. That's an additional property. And then a smooth Koopman eigenfunction, if I plug it in here as a phi, UT phi is E lambda T phi. This is the equation that the eigenfunctions satisfy. So phi dot is equal to lambda phi. So when you exponentiate this, you get that phi at time t is e to the lambda T phi. So through this calculation here, I get that this must be equal to lambda phi. So you get phi dot is equal to lambda phi, right? That's the equation that I just wrote. When you write down Koopman eigenfunctions, they have an exponential evolution in time. That is their property. That is useful. So you basically linearize the system. But here is an interesting point. If you have uniform conditions, so under technical conditions that you need to check in every case, you might have the property that the Koopman operator group or semigroup is exponent of AT, which A is an operator. How do we define that? As you know, This is the same as doing the Taylor series of the standard exponential. So you sum from 0 to infinity. You take this operator to the kth power, multiply with 2 to the k, divide by k. And this is guaranteed to converge in the case that I've just described, right? So you have this exponentiation thing, which...
Sorry, I'm going to ask a really stupid question here.
No.
This eigenfunction equation is really bugging me.
Yes.
You know, you've got an eigenfunction phi for your t. How do you know it doesn't depend on t?
Now this is actually a really nice question. So you have phi dot, that is the change of the function in the direction of the vector field, yes? Phi itself is a static object. It's just an observable. That's the picture that you can have in your mind. It's just a static object. What you're talking about is take an initial condition, find out how much the function changes in the direction of the vector field, and make that change, pull it back to the initial condition. So an eigenfunction is a static object. Yeah? But if you look at its evolution, so
I mean, but if
X.
I look at this formula that says UTG of x is G of
Yeah.
ST of x. So if I say G of ST of x is lambda times
Yeah.
G of x.
for every t, UTG is just a function of x.
But what, I mean, if you say G of ST of x is lambda times G of x,
Yeah. Maybe we can leave this for right after the lecture, okay? Because it is a static object, so I can describe it in some more detail. Anybody else wonders about this question right now? That phi is the static object?
Is the question possibly whether you get, so say you take U2, whether you get all of the eigenfunctions of U2 by squaring the eigenfunctions of U1?
I don't think that's the question, but the question is just,
Well, because if the answer is yes, then you don't have to worry about time.
I mean, never worry about the time dependence. Phi itself is a function, is an element of the function space on M, right?
But it's an eigenfunction.
It doesn't have time dependence in that sense, but it has time dependence in the sense that it changes along the trajectories of the underlying
But
field.
it's an eigenfunction of an operator parameterized by T.
Right. Oh, I see what you're saying. Better. Thank you, Matt. So the answer to that is, interestingly, if your U, T, is a group, then for every T, the eigenfunctions are exactly the same. That better? All right. Thanks. Thanks, Matt. All right. So what I'd like to do now is give you two things. One is the description of linear systems using this exponentiation. And for that, we're going to have to change the perspective a little bit. And the second one is I'll derive what is called Lie series in geometry from the operator theoretic point of view. And you will see that that is an expansion that is kind of interesting in itself. So we have at the top the evolution of a vector G. Now, intentionally, I put in G of P in there. And that is to emphasize that G is just a function that depends on the point in the field, P. I'll come back to that. So if you exponentiate, as I've done at the top, and if you take a look at what A is, so remember A is F dot grad. Yeah. Then you need to put that A, which is an operator, on power K, and that's the expansion that you get. So let's try that on a linear system. X dot is equal to C of X. Then A is Cx dot grad. F is just Cx, right? So the dynamics that we are looking at is linear. X dot is equal to Cx. Now, grad X itself is identity, right? You're differentiating your coordinates, your state coordinates with respect to themselves. So that's just identity. Then AX, you just take CX dot grad X. This is identity, you get CX. So far, so good? Now, this is just a repeat of that operation. And every time you raise an exponent, you're going to get an identity. So you end up with this formula, which you know and love from solutions of linear equations, right? It's just the sum from k is equal to 0 to potentially infinity, k to tk ck x of p, right? Truncated to the finite version by just using the standard algebraic relationship of matrices. But the point is, this x here is not what we're used to call a coordinate. It's actually an observable. So we're turning things that are, standard things on state space coordinates into observables. If you do this for an arbitrary f, you can expand this to write it as, at time t, we start at x of p plus f of p times t plus this convective term t squared over 2 and so on and so forth. I don't know if people recognize it, but this is exactly the least serious solutions of an arbitrary differential equation satisfying, uniqueness existence type conditions. So not x dot is equal to x squared. but now this is useful. I mean, if you look at least series and where they're used, for example, in celestial dynamics for satellites and things like that, the motion, then numerical integrators for short time can be actually based on this. But it's kind of an interesting fact that you can get from a functional analytic version of this down to Lie series. Now, this is an equivalent of Taylor series. I'm now going to go into a different type of expansion, which is going to be more exponential in time. So short-term Taylor series, long-term exponential expansions. All right. Before I do that, let me generalize the idea that energy is an eigenfunction of an arbitrary Hamiltonian system. So there is quite a useful concept in dynamical systems, and that is the concept of partitions. A partition is just a partition of state space into sets, right? An invariant partition is partitioned into sets that are invariant, that is invariant under dynamics. So if you're in a measurable context, if you had some set B in the partition and T inverse of A is B, for every set A, you have to have the relationship that T inverse of A is B and B is in the same partition. Okay, so orbits give an invariant partition, but if you have a rotation on the circle with an irrational jump, orbits might not be as useful as they are in general, because of course they're dense on the circle, and so how do you separate two orbits, right, with a finite measurement? And in that particular context, a useful partition is of course the whole set, the whole circle, and the empty set. But as we already noticed, the energy for a Hamiltonian system, this is just 1 degree of freedom, satisfies h dot is equal to 0. Note, h dot is equal to 0, if I write it as phi dot is equal to 0, is just an equation for an eigenfunction of the Koopman operator at eigenvalue 0. So energy belongs to the eigenspace at 0. And it is an easily proven proposition which says that if phi is any Koopman eigenfunction of a continuous time system, x dot is equal to f of x, with either a flow Tt, or it's an eigenfunction of a map T from M to M, the level sets of that eigenfunction are giving you an invariant partition. Right? So the energy partition is one of those, but there are others, and as you will see, the known concept of isochrones, basically a nonlinear phase in dynamical systems, comes out of a Koopman eigenfunction. The isostables, which is a new concept that didn't exist before the Koopman we expanded Koopman theory to dissipative systems. That's a novel concept in dynamical systems that also gives you the geometry of the underlying dynamical system. This is the first time that we're kind of really seeing a glimpse of how finding eigenfunctions will give you geometry. So let me show you on an explicit example. Take r dot is r1 minus r squared, right? That's one-dimensional, and that is just going to have a fixed point at 1. This is r. And then theta dot is omega, so that's just spinning. So if you want to find the eigenfunctions of this system that is globally stable to limit cycle at 1, you write e to the I theta. I said it's important to start with complex analysis, the reason being that eigenfunctions can be complex. And e to the I theta is the function that describes the unit circle. And the other one, you compute a little bit, and you find this phi s to be 1 minus r squared over r squared. The fact that it blows up at 0 is actually important. If you're on that state space, the eigenfunction has to linearize it somehow. You will see in a second. And so it has to blow up at the equilibrium that is unstable. So that's not a bug, it's a feature to a certain extent. And then you get phi c dot is I omega phi c. Very easy to compute, just take the time derivative. Theta dot is omega, and so you get I omega phi c. And then phi s dot is minus 2 phi s. You could say, well, I have phi c complex conjugate as well, but that's going to give you pretty much the same relationship. So you have two eigenfunctions. You have two eigenfunctions. The level sets of this one are just the rays, right? They're just, that's constant theta. The level sets of the other one are constant r. So we just got a polar coordinate description of this system, and the underlying coordinates, quote unquote, remember they are observables, are the eigenfunctions of the Koopman operator. The Koopman operator actually gives you the geometry to this notion of isochrones and isostables. Isostables tell you something about how things converge to the attractor. Isochrones tell you about the phase, where on the attractor they're going to converge to. One important point. Sometimes a conundrum arises because people say, hey, you say, oh, you linearized your system. Every textbook of dynamical systems, is literally a quote from someone, I'm not going to mention names, says that this only has a fixed point at x equals to 0, and so this cannot describe any other dynamics. Does anybody see the resolution of this particular issue? I mean, it looks like an issue. No? Yes? Are you laughing because you know the name? Okay.
Because I can't see it.
Oh, look at this. This is not your normal monotone state space coordinate. It's a complex function on your state space. This set of functions maps your plane to a cone with a singularity at the bottom. They are linear equations, but they are linear equations that are evolving dynamics on a very nonlinear object. Those equations don't have to have only a fixed point as the equilibrium. They can have pretty much anything, depending on how complex your topology is. And so, this particular conundrum is solved. I hope you see it now. Right? So they're only linear because you can write, the linearity of it is, okay, the right-hand side is linear in whatever I'm writing down, and you can also write exponential evolution. But the functions themselves, first of all, one of them is not real. It's complex.
Sorry, and then I couldn't see the board, what you were writing.
Oh, okay. That's excellent. There we go. I wrote that, and that has only, if x is what we classically think about Descartes coordinates, then this has only a fixed point at the origin. All right. So eigenfunctions are useful. Let's consider them for linear systems. Steve told you about Clancy Rowley doing a sabbatical and connecting DMD to the Koopman. What he didn't tell you is that we played a lot of music. He's a fantastic pianist, actually. During that time, I'm kind of balancing on whether we did more music or Koopman and DMD. I'm not sure. Yes. So I wonder what would have happened if Matt was there to play drums, but we'll find that out in some future conference. Anyhow, we have now x dot is equal to ax. Thank you for pointing out that you didn't see it. I don't know if you see it, but it's linear. So we'll take the complex inner product. So we are complex conjugate in the second argument, right? So this is sesquilinear. It's not purely linear. So what happens is if you include your scalar, you multiply your y with a scalar, it comes out as the complex conjugate. That's the only change. So if you define phi j to be inner product of x with wj, where wj is the jth left eigenvector of A, then easy to prove, this is an eigenfunction. So take phi j dot, you get ax wj, that's x inner product with A star. Yeah, wj, A star wj is lambda j complex conjugate wj. Complex conjugate goes out as its complex conjugate, right? Lambda j itself. And then you multiply phi j, so phi j dot is lambda j phi j. That's our eigenfunction equation. Linear systems like x dot is equal to ax have linear eigenfunctions, right? They're linear in x. Okay, so one interesting thing that comes out of this, that when we study linear systems, if we expand our x in the inner product of x and wj, and vj's are our right eigenvectors. Did I say right or left here? Hopefully I said left. Right eigenvectors, you get that phi j of x in there. Now you take your group acting on the coordinate functions. The Koopman operator always acts on observables, so I had to write the big X because that means it's some function of x0. Then I get e to the at x0. I've already shown you the expansion. I get j is equal 1 to n, e to the lambda j t, phi j of x0 vj. It feels like there is no surprise there, but there is one. When we all learn linear systems, we get told, oh, it's this thing, that's the eigenvalues of A, and it's this thing, and that's the eigenvectors. And then there is something that depends on initial conditions. Yes, this is at least my generation, right? I hope the next generation just gets trained by being told that's a Koopman eigenfunction. That's a Koopman eigenfunction of the linear system. So when you have, let me be very precise, if you have linear systems on a linear function space, we have to define the function space, not L2, but space of linear functions, right? In that particular case, you get this spectral expansion, and that spectral expansion consists of what is called now called the Koopman spectral triple. Eigenvalues, eigenfunctions, guess what these are? Koopman modes, what we call today Koopman modes, right? I call them shape modes, but became in the DMD paper with Clancy, we named them Koopman modes. The beautiful fact in Koopman theory is that in the case of linear systems, the objects that you know and love, like eigenvectors, are in fact Koopman modes, right? And you can generalize the concept of eigenvectors to Koopman modes when you go to nonlinear systems. That's a really nice fact. Now, eigenvalues and eigenfunctions are properties of the operator. The operator defines them. They don't change. The modes are the properties of the observable and the operator. So they're projections of the observations you're taking onto the eigenspace, right? So if you, in general Koopman operator context, we are going to ask whether we have an eigenspace. In general infinite dimensional context, you don't need to have eigenvalues. But if you have it, then Koopman modes are projections on eigenfunctions. Now, if you take your observable to be some matrix multiplying x, then your Koopman modes are going to be that matrix multiplying eigenvectors. So now they're not eigenvectors anymore. If you're observing something else than just your state, then the modes are going to change. Harmonic oscillator revisited. This is actually another fun thing if you're going through the basic calculations and you're writing harmonic oscillator and say, well, there is nothing new to discover. Remember, I just told you something that kind of hit us when we first looked at it, that constant is a Koopman eigenfunction. Here you have x1 dot is x2, x2 dot is minus omega n squared x1, omega n is your natural frequency. Given the expansion that I gave you, that I'll just show it, that one from the previous slide, this one, you don't need to do any calculations to start with. You can just compute you need to do just one thing, compute the eigenvalues and the eigenfunctions, right? There are prescribed formulas for these, and you write that. You know that's the solution. You don't need to do anything else, right? There is a solution. That's what it is. You can ask the question, what are the eigenfunctions? Yes?
So if your observable is the state but multiplied by another matrix, you're saying that eigenmode is just some matrix multiplied by the eigenfunction.
Yes. Take a look. The proof is easy, right? So take this capital X and multiply it by a matrix C. That's a scalar, that's a scalar, that's a vector. C just ports through and multiplies the vector.
So from a usage perspective, then, would it be better, because it's basically saying your observer was a linear function of the state. Would it be better to have nonlinear function of the state?
I'll get to nonlinear functions in 2 slides.
Okay.
So we'll talk about it.
There's one other really nice way of seeing it. Worth thinking about. You can think of the beta as expansion coefficients. So you have a basis of these eigenfunctions and you have expansion coefficients.
But I feel like you're getting the same information. Like if I want to know both the Koopman mode and the Koopman eigenfunction, I don't want the Koopman mode to
So
be.
you have a Fourier series. The eigenfunctions would be the Fourier modes, and then the series, the coefficients would be the Koopman modes. I should have said Fourier functions.
I'm just curious, like if you want the observables to be some other crazy thing of the state, or if you're like, I really should design it.
Let me give you an engineering perspective. In principle, in engineering, honestly, you want everything to be linear. You can design wonderful things and predict and do everything that you want. Now, the nature is not that, so you have to deal with it. Most commonly, you're dealt the observables that you have. Your question is interesting because, and I'll come back to that in one of the future lectures, is if you pick specific observables, even in the chaotic system, you can actually get good predictability for a while. So there is a reason for saying, in an engineering sense, hey, can I pick certain observables? But most commonly, you're just faced with the problem of, I have these observations. These are the sensors that I have. I need to represent that, right?
But the whole power of neural networks these days is to have really weird nonlinear functions.
Yeah, and there is, and Steve is sitting here. He ported some of that into the Koopman world in the sense that we have deep Koopman, which is the context in which you're finding observables to represent, to make sure that the dynamics in the embedded space is linear. You're right. As we go on, I think you'll see a little more of this. Okay, so what I wanted to point out here is that find the eigenvalues, that's the solution, and then what's the interesting bit is computing the eigenfunctions. Interestingly, they are a product of R and e to the I theta. By now you might see that e to the I theta itself is an eigenfunction, but interesting bit here is that the R is really related to energy. So energy is just k r0 squared over 2. There's a 2 missing. So one of these objects is constant times energy. The other one is the complex phase, e to the I theta. Remember, products of eigenfunctions are eigenfunctions. So r times e to the I theta is the eigenfunction that comes out. What is somewhat magical about this is in the same way when you learn first that the eigenvalues actually say something about the physics, right? You compute the eigenvalues of this matrix and that tells you the natural frequency. That's crazy. An unnatural effectiveness of mathematics, the unreasonable effectiveness of mathematics in the natural sciences. This is also kind of weird and unreasonable that the underlying, if you separate these two, you get energy and phase, which is, you know, again, any self-respecting engineer that is doing linear or nonlinear oscillations are going to tell you that the energy and the phase are the things that you need to know about. And the Koopman analysis brings those out as objects in the particular eigenspaces, right? All right, you can do more geometry. So it's another, I think I'll need 5 minutes if you guys don't mind. Is that okay? All right. So there's a particularly nice observation. Let's suppose that you have a dynamical system. In this case, it's linear. And you have the stable direction, here's the equilibrium point, the unstable direction, and the center direction, right? Classically, we are taught to think about those as spans of eigenvectors, yes? So there is an eigenvector that gives you the stable direction, there is an eigenvector that gives you the unstable direction, and there's an eigenvector that gives you the center direction. But you go to nonlinear systems, and that completely falls apart. The only thing that you can do is local center stable, unstable manifolds. Take a look at this. So x, e, and x0. I'll write it as a Koopman expansion. J is equal 1 to n, e to the lambda jt, pi j of x0, ej. So sure, if you pick a particular stable eigenvector, and your initial condition is right in that direction, right? Here is your initial condition. Your trajectory is going to decay to the fixed point. But equivalently, if you pick the initial condition such that it nulls all the unstable and center dynamics, so the zero level sets of these eigenfunctions, combined zero level sets. If this is 0 for that x0, for all the center and unstable directions, then your initial condition must decay because the only thing that's going to be left in this is j is stable. Meaning lambdas for that j have a negative real part, yes? So the stable subspace is generated by zero level sets of unstable and center eigenfunctions. Now that ports perfectly to the nonlinear case. So I would say we've been reading this equation wrong for a good number of years. That is what ports perfectly. The eigenfunctions, zero level sets of eigenfunctions, in particular the principal eigenfunctions, that are eigenfunctions that are associated with this linearization, that gives you the center stable and unstable manifolds, as I'll show you in the coming lecture. I'll expand this a little bit and tell you that you can do this completely in general in the case when geometric multiplicity is not equal to algebraic multiplicity. In that particular case, you need to care about the algebraic multiplicity, mj. You're summing now over eigenvalues 1 to s and over multiplicities 1 to mj. But the expressions look very similar. There is quite a bit of work to come down here. But these phi jk's are the generalized eigenfunctions. So you find generalized eigenvectors of the matrix that span the subspace. Then you multiply those with x0 in this complex inner product. and you get this expression here. Of course, what shows up is algebraic terms on top of the exponential terms that we had before. And then these objects here are called the generalized eigenfunctions. It is, some of this work is series work, so the expansions here, not series, but series. Some of this, it takes a little bit, but it takes about a page. And it's actually quite elegant in my view, in the sense that if you look at Hirsch and Smale, that's how I took dynamical systems, didn't I? And if you look at Hirsch and Smale, it's about 50 pages to get to that. So it gives you some elegance if you want to derive even simple things of this.
Igor, I don't know if this is the time to mention, but we talked about the situation where your representation there is really a good one, but all the lambdas are unstable. And then the system goes to another place where that's pretty good.
Yeah.
But they're unstable there too. So the system goes.
So
are we going to get to there?
Yes, we'll talk about the multi-stability as well.
Okay.
Yes. All right, the question was on nonlinear observables on linear systems. I already showed you that, right? I had Z, and I had nonlinear observables Z to the n, nonlinear eigenfunctions. So I showed that. Here's what you can do in general. So you start with UTF. So evolution of your observable F. It's an arbitrary observable. And you want to show it as a function as x1 to xn, right? But what's convenient is if you have n eigenfunctions, the principal ones, which in this case, in the linear systems case, are just inner products of x with wj. That's what we're going to call the principal eigenfunctions. In this case, you can replace your original coordinates with the eigenfunction coordinates, phi j. If you're in the right space, which is, for example, the space of entire functions, and your f belongs to that correct space, I'll come to functional spaces, then this has a Taylor series. So you just write the Taylor series. Phi j, phi 1, phi 2, phi 3, phi 1 times phi 2, phi 1 squared, and so on and so forth. You write that, and then you port it back to x1 to xn. You have your solution, and here it is. The solution is the expansion over all the indices, n1 to nd, products of eigenfunctions, of principal eigenfunctions, yes? Eigenvalues are sums over integers of your principal eigenvalues. This is a nonlinear observable in a linear system. That, and then you have this thing here, which is obviously from the Taylor expansion. It's a derivative, an index derivative of f with respect to phi's evaluated at 0, because the eigenfunctions, if lambda is stable, negative real part, have to be 0 at 0, right? They decay to 0. So x is equal to 0 is phi is equal to 0. That's your Koopman mode now. Right? The Koopman mode for index n. So analytically, for this case of nonlinear observables on linear, you can actually get that particular expansion. This is interesting. It's just like Fourier series for nonlinear systems, right? You have omega, 2 omega, 3 omega, 4 omega, or if you have 2 omega, omega 1 and omega 2, n1 omega 1, n2 omega plus n2 omega 2. This is the Koopman version of this. So you take your principal eigenvalues and you multiply them by positive integers, and you're going to get your eigenvalues. In general, what does that look like when you compute it? For j is 0 to 4, lambda 1 is minus 0.5. Lambda 2 is lambda 3 complex conjugate minus 0.2 e to the I pi over 4. These two, you sum all of or these principal ones over all the integers, and you get a lattice of this kind. So nonlinear, in a sec, nonlinear observations on linear systems will give you that lattice. Computing that lattice, if you're not working in a correct space, as I said, you need analytic, you need some analyticity for this to work precisely, and I'll define these precisely. If you're working in L2, it is likely to be a mess. Yes.
I was going to ask about resonances in. That's why you have the generalized eigenfunction.
Thank you for that question.
Yes.
Thank you for that question. I forgot to say that I'm going to simplify that expression and not have the case in which algebraic multiplicities and geometric multiplicities are different. You can derive, as you might guess, the formula very easily if you have resonances as well, and that in the context of linearization is actually quite important. Everything does go through. The algebraic work gets pretty heavy, as you might, guess. There is more sums to deal with.
But it doesn't break things like
It doesn't break things all the way down to C1, where everything breaks down, right? Well, everything still works in Hartman-Grobman type of stuff. Beyond that, C0, not very pretty. But yeah, up to C1, at least if you're interested just in the first order stuff, things are going to work. I think that's my, okay, I went a little long. So we talked about 3 classical views. We talked about eigenfunctions. I exhibited this analytically on linear systems with nonlinear observations, potentially. Spectral decomposition, we introduced the spectral triple. Now we're going to work, we already worked the linear systems in the general non-diagonal case. I actually ported this to this lecture and forgot to erase this. So we are already there. Sorry for the 7-minute extension. We're going to get the nonlinear systems via linearization and conjugacy in the next one, and you will see that this type of analysis very easily ports to limit cycles, to limit tori, and then we hit the wall with chaotic attractors, and we have to work harder, because in that case the separation between these simpler cases, completely manageable by the idea of conjugacy, and the chaotic dynamics is that the Koopman operator develops what is called a continuous spectrum. Infinite dimensional operators don't have clearly just eigenvalues. If they have any, that's good for you. Eigenvalues are good. Now, if you don't have any eigenvalues, there are a number of people in this room that have done really, really nice work. In that case, Gary has done some others. All right, that's where we are. Thank you. Questions?
What space are you using to construct the lattice eigenvalue?
Say it again.
What space are you using to construct the lattice eigenvalue?
And so in this particular linear case, and that is the only case, the standard what is called Fock space, which is, so the kernel is e to the z squared over, e to the x squared over 2. So that's a really nice question, because I struggled with that question for the non. So if you read through the functional analytic literature on composition operators, you will find that they knew that the Fock space is only closed under Koopman dynamics for their systems on the disk in the case when the system is linear. That's really interesting, right? Now, there is a simple solution when we go nonlinear, but I'll present it in gory detail. There is something that I call the modified Fock space, in which you can do this kind of a thing. This is the standard Fock space. You can get these results, right? And so I'll talk about modified Fock space, and it kind of goes to Tony's question as well, because that's actually kind of important when you're looking at expansions, and why when you go between 2 different fixed points, one expansion might break and you get another one coming in. Any other questions? Okay, so far so good. Thank you.